Hey everyone, and welcome. Have you ever looked into a glass of water and noticed something just looked a little weird? Or maybe you've stared up at the night sky and wondered why the stars seem to twinkle? Well, today we are diving deep into the fascinating physics behind these everyday illusions. We're talking about refraction, the amazing bending of light. All right, let's jump right in with the classic example that has probably made you scratch your head more than once. You take a perfectly straight straw or a pencil, stick it in a glass of water, and bam, it suddenly looks like it's broken right at the surface. So what's the deal? In this explainer, we're going to solve this very mystery. Now, to get to the bottom of our bent stick problem, we first have to understand the fundamental principle that's at play here. So let's start with a big question. What exactly is light refraction? Think of it as the science behind this little bend in our perceived reality. Okay, so here's the official definition. Refraction is just the change in direction that light takes when it passes from one transparent material, or medium, into another one. Like when light goes from the air into water, or from the air into a piece of glass. It's a phenomenon that happens right at the boundary, that surface between the two different things.
But why does light bend in the first place? What's the core reason for this sudden change in direction? Well, the answer is actually pretty simple. The single culprit is a change in speed. Turns out, light doesn't travel at the same velocity through everything.
Out in the vacuum of space, light is just flooring it, hitting its universal speed limit, a mind-boggling 300 million meters per second. But the moment it enters a substance, like water or glass, it has to slow down. We call materials that are better at slowing down light optically denser. So glass is optically denser than water, and water's way more optically dense than air. Okay, so light changes speed. We get that. But the bending isn't just random, it follows some very specific, very predictable rules. So in this next part, let's look at the rules of the road that tell us exactly why and how light bends the way it does. And the key to all these rules is a concept called the refractive index. It's often shown with the Greek letter mu. Now, don't let the name scare you. It's really just a number that tells us how much a medium puts the brakes on light. The higher the refractive index, the more optically dense the material is, and the more it's going to slow that light down. And this chart makes it super clear. Take a look. Air has a refractive index of pretty much 1, which means light barely slows down at all. Water is a bit higher at 1.33, glass is up at 1.5, and then you get to diamond with a massive refractive index of 2.41. That means light travels more than twice as slow in a diamond than in a vacuum. And it's this drastic slowing of light that gives diamonds their famous sparkle. So how can we calculate the exact angle of the bend? For that, we turn to a master rule called Snell's law. You don't have to be a math whiz to get the main idea. It's basically a formula that proves the amount light bends is perfectly predictable and directly related to those refractive index numbers we just saw. This is the law that lets scientists and engineers predict the exact path of light through any lens or prism you can imagine. Let's actually see these rules in action. First, you have to imagine an invisible line drawn at a right angle to the surface where the light hits. We call this the normal. As you can see on the left, when light enters a denser medium and slows down, it bends towards this normal line. Now look at the right. The opposite happens. When light speeds up as it enters a less dense or rarer medium, it bends away from the normal. The takeaway is pretty simple. Slow down, bend in. Speed up, bend out.
All right, now that we have the rules down, let's have some fun with it. Let's trace the path of a light ray as it navigates a couple of common glass shapes, and we'll put our new knowledge to the test.
First up, a simple rectangular block of glass. Light comes in, it slows down, and it bends towards the normal. It travels through the glass, and then it exits on the other side. As it exits, it speeds back up and bends away from the normal. Now, because the two sides of the block are perfectly parallel, the bend on the way out is the exact opposite of the bend on the way in. And what's the result? The light ray comes out traveling parallel to its original path, just shifted sideways a little bit. We call that lateral displacement. But what if the sides aren't parallel, like in a prism? Now it gets interesting. The light ray bends when it enters, just like before. But when it goes to leave, the exit surface is at a totally different angle, so the bend on the way out no longer cancels the bend on the way in. A prism actually forces the light to change its direction for good. This is called deviation. Now, this whole principle of bending light can lead to an even more extreme and, frankly, incredible outcome. A situation where light can get trapped and can't escape at all. Let's talk about the point of no return: total internal reflection. Okay, let's walk through this step by step. First, this whole phenomenon only happens when light is trying to go from a denser material to a rarer one, like from glass back into air. As we increase the angle that the light hits the boundary, the refracted ray bends more and more, getting closer and closer to just skimming the surface. Then, at one very specific angle, called the critical angle, the light zips perfectly along the boundary. And if you increase your angle just a fraction of a degree more, the light just gives up. It can't escape, and it reflects perfectly back into the denser material. This here shows us that exact tipping point. The light ray is hitting the surface right at the critical angle. And notice the refracted ray. It's not really escaping, it's just traveling perfectly along that boundary line at 90 degrees. This is the absolute last chance for refraction to happen. And here is the magic. The angle of incidence is now greater than the critical angle. Look closely. Where's the refracted ray? It's gone. There isn't one. The light is completely reflected back into the glass, just as if that boundary had turned into a perfect mirror. That is total internal reflection. So, we've covered the physics, the rules, and even the point of no return. Now, let's bring this all full circle. Let's use what we've learned to start spotting the illusions that refraction creates in our day-to-day lives. I'm telling you, once you know what to look for, you'll see it everywhere. It's the reason a swimming pool always looks shallower than it really is. It's why a coin at the bottom of a cup seems to magically lift up when you pour water in. It's even why stars twinkle, because their light is refracting through all the turbulent layers of our atmosphere. And, of course, it's the answer to our original mystery. And this image explains it all perfectly. Light rays bounce off the part of the stick that's underwater and travel up to our eyes. To get there, they have to go from water into air, so they speed up and they bend away from the normal. But here's the catch. Our brain is hardwired to assume light always travels in a perfectly straight line, so it traces these bent rays straight back, not to where the stick actually is, but to a shallower, virtual position. And that's why the submerged part looks like it's lifted up, creating that classic bend at the water surface. So there you have it. From a bent stick to a twinkling star, it all comes down to this simple, predictable bending of light. But I'll leave you with this final thought. We just saw how total internal reflection can literally trap light inside a material. So if a high refractive index and that trapping effect can control light, what does that look like in the real world? Well, it looks like the fire in a diamond, or the technology that powers the entire internet. And that's the power of knowing how to bend a little light.